What we can go on now is to see what we should do in the case of a control volume and not a control mass. So let us say we have a general control volume as is shown over here, some arbitrarily shaped control volume. This is a real control volume, so it does not undergo ideal processes. When this control volume undergoes processes, its entropy changes. It has some mass, and its mass can change. The rate of change of mass is dm by dt of the control volume. It has some mass coming in, mi dot, some mass going out, me dot. It has some energy. The rate of change of energy of the control volume is given as dE by dt of the control volume. It has fluid coming in, which is bringing in energy. Fluid going out is taking out energy as well. The control volume itself can be moving, which also will be reflected in this. It has heat coming in. It can have more than one source of heat. Since we are going to look at the second law as well, and we are going to look at entropies, we need to take into account the temperature at which each source of heat is giving in heat. So each of those is given as some q dot of j, where if I have more than one source, this is q dot 1. If I have another source here, that would be q dot 2, and so on. The temperature corresponding to that is like T1, and then it would be T2, and so on. In addition, the entropy of the system can change, of this control volume can change. So the change in entropy is given as ds by dt of the control volume. This control volume can do work. It does work at a rate of w dot cv actual, and that is something we can find out. And because this does not undergo ideal processes, what we see is that there is entropy generation in this control volume, and the amount of entropy generated is given as s dot generated for the actual process. So this is essentially our control volume. This control volume has interactions with the surroundings, which is at some temperature of T0. So if we write the mass conservation, we have done this expression, we have seen it several times. We have written it for many control volumes. We see dm by dt for the control volume, rate of change of mass, is equal to sigma of rate at which mass is coming in minus sigma of rate at which mass is going out. We can of course have any number of inlets and outlets. What we can also write is the first law for this control volume, which is also something we have seen before. So we see the rate of change of energy of the control volume, dE by dt for the control volume, is the rate at which heat is coming in. We used to generally write this only as q dot earlier, but since we are going to look at the second law as well, it is not sufficient for us to club all the heat transfers in and out. We need to know the temperature at which each happens. So this time we are now writing it with sigma of q dot j, so that we know each of them separately. So we have q dot minus w dot of the control volume during the actual process, plus sigma mi dot into whatever energy is brought in the form of enthalpy, kinetic energy or potential energy, minus sigma of the mass flow rate going out into whatever energy it's taking out in the form of specific enthalpy, specific kinetic energy or specific potential energy. All of these of course are specific values. So this is the first law. The only difference between what we had been writing earlier and now is that we have separated out this q dot j and as a summation of different heat transfers, because we need to know the temperature at which each happens. We can also look at the entropy equation, which we saw in the previous class as well. So we have ds by dt for the control volume, rate of change of entropy for the control volume. The entropy change is because of heat transfers. So we have q dot j divided by the temperature at which each transfer happens. If these are negative, if this is losing heat, then the entropy of this control volume will go down. If it is gaining heat, the entropy of this control volume will go up, because we know q is positive when heat comes in, which means this will be positive. Q is negative when heat goes out, which means this will be negative. So because of this term alone, the contribution will be either positive or negative here. In addition, because we have mass coming in and going out, it can bring in or take out entropy. So we have sigma mi dot into the specific entropy which is brought in by this mass, minus sigma m dot e into the specific entropy which is taken out by this mass. In addition to this, because this is a real control volume which undergoes actual processes and it is not ideal, we have entropy which is generated because of irreversibilities, because of friction, because processes are not quasi-static. because of heat transfer, any other heat transfers which are not shown here, and so on. So we have S.gen act. Actually speaking, all heat transfers should be considered here, so this would be due to irreversibilities alone. So we have the entropy equation as well over here. What we are going to do is to compare this control volume which we just saw with a similar ideal control volume which undergoes a reversible process between the same states. So let me just repeat that. So we are looking at a similar control volume, but our new control volume which we are looking at is ideal, which means it undergoes fully reversible processes. But we are going to see what happens when the ideal control volume has processes which start at the same state as the previous actual control volume and also ends at the same state as the actual control volume. So this is something we need to note down carefully. So the end state and the start states are the same and all inputs are the same. So the mass conservation equation is essentially the same as it was before. So there is the same amount of mass initially, same amount of mass finally, dm by dt is the same, m dot I, m dot e are the same, so mass conservation remains exactly the same. dE by dt is the same because we have the same initial and final states. So the rate of change of energy with respect to time is the same. The initial state is the same, final state is the same, it's happening over the same time. So dE by dt is the same. ds by dt is also the same because same state means entropy of the actual control volume and the entropy of the ideal control volume should be the same. So the initial entropy of both are the same, the final entropy of both are the same, it happens at the same time, so ds by dt is the same. So what we see is in the equations we had here, the left hand side is the same for all of these cases. So the left hand side is the same for both the actual control volume as well as the ideal control volume. This part is the same for both actual and ideal control volumes. For these two equations, the left hand side is the same. Now if we look at this equation over here, the entropy equation, what we see is that this is the same because the states are the same. These are the same because the states are the same. This part has the same amount of heat transfer, but what we see is this term was there for the actual control volume, which is not there for the ideal control volume because the ideal control volume undergoes a reversible process, so there will not be any entropy generation. So I need to get the same ds by dt which was there in the actual case, but I have now this term which is the same, this term which is the same, this term which is the same, but I do not have this term. So there is some part missing here in order to get the same change in entropy. So in the ideal control volume, if I needed to get the same entropy as previous case, what I see is I need to add some stuff to compensate for this which is missing, because this term is always positive and it is now 0 in the ideal case, but in the actual case it is positive and a real value. So I need to add something which gives me the same change in entropy as this S.gen so that I can get the same final state. Now we see that there are only two ways of increasing the entropy once the mass flow rates are fixed. So we can either increase the irreversibility and then increase the entropy, which was what was happening in the actual case, but now we are looking at an ideal case, so that is not something we can do. The second way of increasing the entropy is to add heat. So if I need to get the same change in entropy for the ideal case as in the actual case, what we need to do is to add heat so that this goes up, the entropy over here goes up. So if I'm going to add heat here, that also has to be reflected in the energy equation. So that is what we are going to see. So there must be reversible addition of entropy. This is a reversible process, this is an ideal process, so it has to be reversible, but there has to be addition of entropy. So that can be achieved by adding heat reversibly. Now this heat can be from any source. What we are going to assume is that this heat is from the ambient. It has to be reversible. That is easy if we have a constant temperature source, which is, for example, the ambient. So let the amount of heat we need to add be Q dot reversible, Q naught dot reversible from the ambient, which is at a temperature of T naught, and this amount of heat needs to also be accounted for in the energy equation. And because the energy equation changes, what we see is the work which we get will also be different compared to what it was in the actual process. So in order to reach the same final state, because the processes are reversible over here, we need to have something which adds entropy, and that is in the form of this heat. It's a reversible heat addition which can also be removed if we want, and because we are adding more heat here, we are also going to get more amount of work in this case. So if we compare the corresponding terms, in the actual control volume, we had this term which accounts for entropy generation due to irreversibilities. In the ideal control volume, what we are doing is, we are, instead of having this, because this is 0, we are adding Q0 reversible, which happens at a temperature of T0, and the corresponding entropy change due to this is Q0 reversible by T0. Therefore, these two terms are equal, so I can find out Q0 reversible, which is equal to T0 into S dot gen actual. So this is one expression which I get. Now secondly, if I look at the energy equation, what I see is minus W dot of the CV in the actual case will now become Q dot reversible from the ambient minus W dot reversible for the ideal control volume. Therefore, the work which is done in the case of the ideal control volume, which is W dot reversible, is whatever work I was getting in the actual control volume, W dot CV actual, plus I now have this additional Q dot reversible from the ambient. So what I see is, in addition to whatever work we had earlier, I will get some extra work which is given by this term if this process happened reversibly. Or in other words, if the work happened irreversibly, I would lose this amount of work when this process is having irreversibilities or friction or things like that. Now the interesting thing over here to note is, the ideal control volume has heat transfer from the ambient even if the actual control volume undergoes an adiabatic process. So the general heat transfer is taken into account by this term. So even if this term was 0 in the case of the actual control volume, in the case of the ideal control volume, I have the Q0 coming in here from the ambient. So in the case of the ideal control volume, there would be heat transfer from the ambient even if the actual control volume undergoes an adiabatic process, as long as the actual control volume was irreversible. So the only case where both these will be adiabatic is when both of them are reversible. In that case, the ideal and the actual actually will have the same process, and you can have an isentropic process in both. So when we put those expressions together, what we saw in the previous slide is that the W dot in the reversible process is whatever you have in the actual process plus Q dot reversible, which happens from the ambient. This is what we had written in the previous slide. Now from the first law, this expression we have in this form, which is shown in light blue over here. So we have W dot CV actual is minus dE by dt of the control volume plus sigma of all the heat transfer which happens plus sigma of Mi dot into whatever energy is being brought in minus sigma of Me dot into whatever energy is being taken out. And now we have this extra term Q dot reversible from the ambient. So in the previous slide, we noted that Q dot reversible from the ambient is essentially given as T naught into whatever is the entropy generation in the actual case. And before that, what we had is, from the entropy equation, we had an expression for the entropy generation, which is essentially ds by dt minus this plus this. So we are going to substitute this expression as well into the equation for reversible work. So over here, in the place of this Q dot reversible, we are going to put T naught into entropy generation term, which comes out to be ds by dt minus sigma of Q dot j by tj minus m dot isi plus m dot e se sigma of. So what we see is that now the reversible work is given as minus d by dt plus sigma of Q dot j plus whatever is the mass flow rate coming in into the enthalpy which it brings minus whatever is the mass flow rate going out into the enthalpy which it takes out plus Q naught in reversible. So that is essentially what we have. We can also rewrite this in this form. We can club together all the heat terms. So we can write this as 1 minus T naught by Tj into Q dot J plus sigma of Mi dot into whatever is the enthalpy which is being brought minus T naught into Si minus sigma of M dot E into whatever is the energy being brought in minus T naught Se, which is the entropy contribution, minus of dE by dt for the control volume minus T naught into ds by dt for the control volume. So we can also write it in this form. This is actually an interesting way of writing it, because this looks like, for example, what we had earlier when we had, for example, a constant temperature source or something like that. This looks like the expression of the work you would get from a Carnot cycle. So you have some heat transfer which is coming at some temperature of J, and it is exchanging heat from here and sending it out to an ambient at T naught. So this is the amount of work which is available when you have this kind of a Q. Then you have mass flow rate coming in, and you have energy which is bringing in, and whatever is the entropy of this mass flow rate coming in, that much of energy is not accessible to us. And then you have again energy which is going out, and this part of it is not accessible out of here. And then you have whatever is the change in energy of the control volume with respect to time, and the change in entropy into T naught with respect to time. So this is an interesting way of looking at it. And of course, if we have devices which have only one inlet and outlet or so on, we can get rid of the sigma of these two sigmas over here. If it is a steady flow device, then we see that any terms with respect to time, any derivatives must be 0. So this will be 0 and this will be 0. And from mass conservation, if we have only one inlet, one outlet, our mass conservation equation becomes dm by dt is m dot I minus m dot E, and we can call both of those m dot I and m dot E as some m dot, because it's steady state and dm by dt is 0. We've done that before as well. So we can divide all of these by m dot in such a case. So we get sigma 1 minus T naught by Tj, and Q dot J by m dot is what we call as Qj. This m dot goes here, so we have enthalpy, kinetic, specific kinetic and potential energies minus T naught into Si as it was earlier. Over here this term goes out, the sigma and the Mi dot goes out, whatever was there in the bracket remains over here, and since it's a steady state, these two terms disappear, and we have a smaller version of this equation which tells us how much of work we can get in a reversible process when we have a device like this.